another character formula, de Mazur character formula. And the reference for this is in Littleman's where in fact the title reads like Littlewood-Richardson rule for symmetrizable Kac-Moody Lie algebras or something like this. Generalized Littlewood-Richardson rule. Okay, whatever, Littlewood-Richardson rule. That is the one that we stated yesterday, right? Stated and proved modulo the isomorphism theorem, right? Okay, everything is modulo the isomorphism theorem, and okay, after looking at it for several days, we have decided we are not going to do the proof of the isomorphism theorem, because already I see the class is less than 20% of what it used to be, and if I start doing the isomorphism theorem, it will be 0. Okay, proof of the isomorphism. So let's do the de Mazur character formula. So this is a very, as Mrigendra was saying, it's very easy and very pleasant. Okay, so that's good news. So there are all the checkings are very easy and very pleasant, and it illustrates a very beautiful property of the paths, absolutely gorgeous property. Okay, which makes, there is just one single property that these paths have, and that property gives you shows that the de Mazur character formula is correct. Okay, that's all this. Okay, so first we need some basics. Okay, so so what is there is something called the de Mazur module. If you haven't seen it, don't worry about it. It is a submodule of V lambda. We have our V lambda. This is a submodule of V lambda. It's also, it's not a G module. Of course, there can't be any submodule of V lambda because that's an irreducible module, but a G submodule of that. But this is what is called a B submodule. Okay, so de Mazur modules. De Mazur submodules. These you can think of being indexed by the Weil group elements. Okay, more precisely, if you want, W mod W lambda, the stabilizer of lambda, or rather, they are indexed by the Weil conjugates of lambda. Okay, there are as many de Mazur submodules as there are Weil conjugates of lambda, but let's not worry about Weil conjugates of lambda. Each Weil conjugate you can associate a Weil group element, maybe not uniquely, unique if lambda is regular, maybe not unique if lambda is not regular, but we will not worry about that. Okay, so given W in W and lambda in P plus, so this V W, I'll put now I have decorated this, I have this additional decoration of W. Okay, so what this is UG of V W lambda. UB, thank you, tensor, that's it. Okay, what this is, by the way, again, too many details about these modules you don't need to understand. No, you only take at face value. I will write down a certain formula, which is called the de Mazur character formula, which gives you the character of these modules. These being B modules, they are also H submodules, and therefore there are weight modules. So you can talk about their characters in the same way. They have multiplicities of weight spaces, right? So I will write down a formula called the de Mazur character formula, and our starting point, which you can take at face value, will be that the character of this de Mazur module is given by the de Mazur character formula. If you recall, that's what we did for while character formula as well, right? When we proved the path character formula, our beginning statement was while character formula. We only checked that character b pi, instead of having the character of the module there, I checked it with the character of the b pi there, right? Similarly here, we will take the de Mazur character formula at face value, and then instead of, we'll just do that for paths, okay, instead. Yes? B is Borel, yes. B is Borel. So it already, when you say lambda, etc., you are assuming that you have chosen a triangular decomposition, or if you are in the Kac-Moody situation, you have started with that, okay, etc. So is this clear? This is the de Mazur module. Okay. Now let's talk about operators which are called de Mazur operators, in terms of which these operators are very simple operators and very nice operators, and the de Mazur character formula is in terms of these operators. Okay. So let me write out. Okay. Now everything from now is very elementary, so you should be able to follow. Okay. This. Okay. So what is this operator? It acts on. They act on. So I take weight spaces, the weight lattice, the weight lattice, and take the Z. I mean here, what I mean is the group ring generated by the weight lattice. So weight lattice I am writing to make, so usually when you write group ring, you think of the group as being written multiplicatively. So each weight, instead of writing the weight, I will write exponential to that. So in order to make the square bracket, huh? I don't. I know, but remember we wrote Z pi. We didn't without a bracket, okay? But in any case, even for the group ring, I am used to not writing. For me, K round bracket G means functions on G. K valued functions on J. This square bracket, right? Yeah, square bracket. For me, that square bracket means functions on G, okay, which means it's a commutative ring, okay. So I'm used to this notation, but it's just a matter of notation, okay. Okay. So these are operators on this. You can think of them as operators on this, okay. So what are these? So for every alpha simple, you write, so this is the notation, okay. So let's say on lambda, where now lambda belongs to this, or should I write, okay, I will write e lambda here, but then I just said e to the lambda is how we think of it, etc. So that I'll go back and forth between these. When I write this, anyway, you make the necessary adjustments. Okay, let me write. lambda minus Okay, there are various ways of writing this. So, let us rewrite it in a few ways. Okay. So notice that given this, so first let us try to understand this operator and various ways of rewriting it, what it actually is doing, etc. Okay? Okay. It's a very important operator. It has some very beautiful properties, some of which we will actually need, we will state and use. Okay. So, observe, I have assumed m is lambda alpha check, right? So, this is an integer because lambda belongs to P. Okay. So, what is this lambda minus m alpha? What could I write it as? So, this is just S alpha lambda, correct. So, I could rewrite this as S alpha lambda, correct. Okay. So, another way of rewriting this would be E lambda plus minus E of S alpha lambda, and then there is a minus alpha, and then there is a 1 minus e to the minus alpha. This is equal to this. Okay. Good question. Good question. Let's, yeah. So, okay, let's work it out and see. Okay. It belongs, the short answer, it belongs because of the geometric series summation. We will work it out. Okay. So, this is equal to, so did you understand his question? His question is, I am writing some expression and I am claiming it is in ZP, correct? I mean, it is not clear at all. I am just writing some numerator denominator, right? Okay. So, you can also rewrite this. Let us write, add e to the alpha, multiply both numerator and denominator by e to the alpha over 2. Okay. If I do that, then I get e to the lambda plus alpha over 2 minus e to the S alpha lambda minus alpha over 2 by e to the alpha over 2 minus e to the minus alpha over 2. Okay. Now, do you recognize that? While character formula for SL2 alpha, that is what it is. It is in fact the while character formula for SL2 alpha. Why? Because what do you write? So, recall the while character formula, right. So, what does it say? Character of V lambda, or which has RHS, recall RHS of, I am only interested in the formula side, I do not care about the left hand side for the moment, of WCF. What form does it have? You write sigma W in W, sine of W, e to the lambda, sorry, e to the W lambda plus rho by W in W, sine of W, e to the W rho, right. Okay. Now, let us put when W is just SL2. Okay. So, let us special, or rather G is SL2, W is just the group generated by these two, which is a group consisting of these two elements. So what does this become? Special case. So specialize. To the case of SL2. Then what does this become? So there are only two elements. There is the identity element. Okay. What is rho? Rho is sum of fundamental weights or half sum of the positive roots. In the SL2 case, how many roots are there? There are two roots. One of them is positive, and it's negative, which are alpha and minus alpha. So what is half sum of the positive roots? Alpha over 2. That's why I actually decided to multiply that by alpha over 2. Okay. So how many elements are there? There are two elements, right? So let me expand it. So identity element, sign is 1. I don't need to write it. E, W is identity. I don't need to write. Lambda plus alpha over 2, right, minus e to the, sorry, I am doing this. So the next element is S alpha, right. So sign of which is minus 1, e to the S alpha of lambda, and S alpha of alpha over 2 is, S alpha on alpha is minus alpha. So that is minus alpha over 2, correct? And here once again, first I write for the identity element, sign is 1, e to, this is also identity, e to the rho, which is e to the alpha over 2, minus e to the, this minus I wrote because I am doing it for S alpha and the sign is negative. So S alpha of alpha over 2, that is minus alpha over 2. You see, that's what I will do. Okay. This is one explanation for this operator. Okay. Now let us also understand what this is actually doing on E lambda. Okay. What this is actually doing on E lambda, which will also answer the question Arithra asked, why the left hand side or the right hand, why this belongs to ZP. Yes? Answers that, but we need to be more explicit anyway. But my suggestion in doing all this is, see, I would, at least for me, I'm speaking for myself more than for you, we write these formulae, and have you ever expanded this out for any particular case and actually written out the terms? Okay, maybe some of us don't need to do it to understand, but I would need to. So I would expand it out and write it for SL3, for B2, etc., and to see what you, okay, that's just, of course, that may not be necessary for many people to do it. So in this case, let's expand it out. Okay. So let's expand. Okay. So E lambda. So so we are computing this. Okay, and M is this. I'm always putting M is equal to this. Let's keep this notation fixed. Okay. So it is E lambda minus E lambda minus M alpha minus alpha by 1 minus E alpha. Right? Right. Let's use some, this is, if you want, this is short notation for the following. Right? What is 1 minus E by our, the only power series of which expansion I know? 1 over 1 minus x is 1 plus x square plus, right? Okay. So let's write this out as that. So 1 minus E alpha is 1 plus e to the minus alpha plus e to the minus 2 alpha plus e to the minus 3 alpha and so on. Did I write that correctly? Ah. Okay. So when I multiply, so this denominator means actually just multiply by this on the numerator, and if I multiply by e lambda, what happens? So let's draw a picture. Lambda is here, right? So what all do I get? Lambda, e to the lambda, e to the lambda minus alpha, and so on, and keep going, right? And what is this? E to the lambda. Where does this thing also start? So let's assume m is positive for the beginning. So m is, let's say, 10. So what is this? M is positive, yeah. Yeah, so it is e to the, where does it start? E to the lambda minus 11 alpha, if m were 10, right? And then everything else. So if I subtract that string from this string, what is left? Up to minus m alpha. So this is equal to, so by a simple calculation, high school algebra calculation, this is e to the lambda plus e to the lambda minus alpha plus e to the lambda minus m alpha, okay, which is of course the character of the SL2 module with highest weight lambda, okay, because I am assuming m is positive, okay. And which, as Arithro says, we should not be surprised because that's the Y character formula also gives us. Okay. So this is what I get. Okay. So this is, even if m is, suppose I put m equal to 0, then it is e lambda minus e lambda minus alpha. So I'll just get one term, namely e lambda itself. Okay. So this is, so if this is if m is bigger than or equal to 0. Correct? So what if m is less than 0? No, this is general lambda, sorry. Oh, sorry, I changed notation. Okay, say there, here lambda, see this is lambda is any element of P. Okay. Okay. Sorry about the, maybe should have used a different letter, but right is, so yes. Because this power series, when I multiply by e to the lambda minus m minus this alpha, it just gets shifted and then everything, right? So the terms that remain are precisely this. Okay. So let's do the negative case. So the lambda is still like this, right? If m were negative, let's say minus 20, right? Minus 20. So what would this become? 20 alpha minus 1. So it would be 19 alpha, right? It would start at 19 alpha. So I have minus e to the lambda minus 19 alpha, correct? and then down, 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 and then e to the lambda plus 19, thank you, and then down to e to the lambda minus alpha, and then e to the, then the rest will cancel, lambda plus alpha, thank you. Correct? So what do I get? This is e to the lambda plus, so I always get confused. So m is negative, right? So I should write minus m, okay, minus alpha, correct. That's easy to see. This is where we start, okay? Plus dot 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 plus e to the lambda plus alpha. Sorry, minus, the whole thing is minus. So it's minus of e to the lambda minus m alpha minus alpha minus e to the lambda plus. Thank you. So when I do these calculations, I never write them out. I just draw dots. That's my problem. I have to try. So let's draw these dots very soon. Okay. Okay. So what it looks like is, so this, let's just do SL2 theory first. So lambda is actually an integer. So lambda is actually this m. You can take lambda to be this m itself. So m is either positive or negative. If it is positive, non-negative, then it gives me the character of that corresponding V lambda, Vm, right? The module with highest weight m, right? If it is negative, then it gives me the negative of the character of minus m plus 1, minus m minus 1, right? This is the negative of the character of minus m minus 1. Correct? If I put lambda equal to, so it's as if I put alpha is equal to 2 and lambda is equal to minus m, lambda equals m. Correct? Let's work it out. So let's draw. So let's draw this picture. The whole of this de Mazur character formula is just an understanding of this picture. So this is the weight picture for SL2, right? So SL2, and I'm used to writing it top to bottom. So this is 0 weight, right? And so there is some weight. So weights are positive weights and there are negative weights, right? So if this m happened to be positive, right? So by that dot I mean I'm thinking of that dot as E lambda, and lambda is the same thing as m, because I'm in SL2, lambda is determined by its value on alpha check.
How do directions change? In the first case, the direction was from here and the direction is going.
Correct, because in the second case I am below, so and it's going up. It's still giving me the negative of the character of a certain irreducible representation. Let's see what is happening, right? Okay. So let's say this was so let's actually.
Sir, sorry, just one minute.
Yes.
So it's just a dual.
Which one?
This irreducible model, the dual of that representation.
It's they're all self-dual. There's only, because there is only one module of that, irreducible module of that representation, of that. So here, suppose m is this, right? Then what is lambda alpha e, what is this? It is all these, right? So which is just all these, right? It is the character of that representation. Okay. So let me denote it by this picture. alpha you think of as 2. Alpha you think of as 2. Yes. When you identify the weights with the integers, then the root gets identified with the integer 2. Correct. The fundamental weight will be 1. Rho is 1 and the alpha is 2. Is this clear? So if I have a single dot and its value evaluates to some positive or non-negative integer on alpha, alpha check, that is if m is non-negative, then the picture I get is precisely this. Okay. What if it is negative? So let's see here. So let's draw a second picture. So let's say at this point, which is 1, 2, 3, negative 3. So at negative 3, if I had this pitch, this dot, how far you are going down? If I start with m, I go to minus m in steps of 2. Okay, that's the irreducible module with highest weight m. Okay, when I say that, I mean this is the character of the irreducible module with highest weight m. Lambda need not be even. Lambda need not be even. Lambda could be odd as well. In which case, if I start with 3, for example, I go 3, 1, minus 1, minus 3. I will always reach minus m because m minus m is 2m. So in m steps of alpha, in m jumps, I will jump from m to minus m. Okay? Okay? Is this clear? Okay. Let's do this. Right? Okay. So what is this? If I act it on, what picture do I get? Yeah. So I start here and right? No. Let's see. Lambda plus alpha. So lambda is minus 3. Alpha is 2. So where do I start?
Yeah, starting is from, I'm saying negative side is downwards, right?
Yes.
So when you look at that expression, left hand side, the same.
This one?
Yeah.
Yes.
So lambda H alpha is m.
Lambda. Yeah, m is negative.
Okay.
Yeah? Yeah, m is negative. So this is the end, this is the top. So the end is lambda plus alpha, which is I start 2 higher. So I start here, it's negative 1. And then go 2, and I must go up to not quite negative of m. Negative of m in this case would be 3, but 1 step less. So which is this. Okay. So the upshot is, so character, lambda, so is equal to character of V lambda. So SL2 case. If lambda is bigger than or equal to 0, sorry for my sloppiness. When I mean lambda bigger than or equal to 0, I hope you understand what I'm saying. It is minus character of V lambda minus m alpha. Okay, how do I write this? Okay, SL2 case, m is equal to I've written this. Okay. Okay. So minus lambda minus 1. Okay, if lambda is less than 0. This is the observation. Thank you. Okay, but one second. There is also, did I do that correctly? Okay. I guess this is not quite this is lambda less than or equal to -2. Sorry. So let me write this. Let me just check what happens if lambda equal to -1. Lambda equal to -1, this becomes character of V -1, which does not make sense unless you interpret it as 0. So let me just change this to lambda less than or equal to -2 and 0 if lambda equal to -1. Okay, just let me do that. You can check this. When lambda equal to -1, that is m is equal to -1, right? This becomes lambda plus alpha minus alpha, which is just e to the lambda. So this is 0. Okay, so that's easy to. Is this okay? So let us encode our use this. So let's just prove two lemmas using this. Yes. Sure. Sure. So the picture in general is here if it is m positive, okay. So this dot, if I have a single dot like this, the image under the de Mazur operator is a sum of dots, right? Because each dot represents a weight for me. Okay, what is that? It starts here in jumps of -2. So this distance is -2, -2, -2, etc. It comes all the way to, if I start with m, I come all the way to -m. Is this clear? All these steps are 2. Right? Okay. So maybe my input, since we have colored chalk here, we say this is the input, right? And if my input, so let us draw a second picture. The input is negative, let's say -m. Okay. Then what happens? I leave this dot out. I start 2 steps higher. So which is what? M minus m, sorry, m is negative. So this is our m. So it's m plus 2. Okay, and in steps of 2, so this is what it goes to. And it doesn't go all the way to -m, but it goes to -m minus 2. -m would be all the way up, starting this from here. But it doesn't go that far, it only goes to this reflection of this. Is this clear? In 2 steps of 2, m minus 1 jumps, or sorry, m minus 2 jumps. M minus 2 jumps. Because see, the simple thing is, if I start at some place, to get to the negative of this, I need exactly as many jumps, or the absolute value of that jumps. If I start at -3, to get to 3, I need 3 jumps. From n to -n is n jumps, or if n is positive, or -n jumps if n is negative. Okay? So yes.
Minus lambda minus 2 what we got. Lambda less than equal to 2.
Yeah.
Minus lambda minus 2 can be interpreted as S alpha dot lambda plus rho minus rho.
Yes. Yeah, there is, you can of course write it out something like that. Huh? Is this okay? Is this picture? Okay. Now let's do the following. Suppose, tell me what, using these two pictures, tell me what the image of so if I have this, what is this? Let's work it out. Suppose it's M, right? I have all these, right? Okay. And I have minus M. I have all these with negative signs. If I add this plus this, it's a linear operator, remember. I mean, I didn't say that, but it's clear. I mean, by definition, it's a linear operator. On the first one, it gives me all these dots, the sum of all these dots. And on the second one, it gives me the negative of the sum of these dots. So when I add these two together, what is left? The end points. So this is just e to the lambda plus e to the minus alpha. Okay? So if, and what if, so that is if lambda is negative, right? What if lambda is, but then it also shows even if lambda is negative, it's the same thing, right? By just, correct? So this is simple. Okay. So with this, what is, let's compute what is lambda square E lambda. Okay. I want to act it twice. No, I don't think so. I don't think so, because I will get e to the 1 plus e to the minus 1. E to the 1 will give me e to the 1 plus e to the minus 1. E to the minus 1 will give me 0. So I get back e to the 1 plus e to the minus 1. No, I don't need to make any exception. Okay. In fact, it's rigged up so that this works correctly. Okay. So let's do lambda square of E lambda. What is it? So what is lambda? So this is lambda by definition. I'm just trying to do this. Right. And what is this? So for, let's assume lambda is positive. Then this is e to the lambda plus e to the lambda minus 2 plus dot 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 e to the, what is that, minus lambda plus 2 plus e to the minus lambda, right? Correct? Okay. So I have to, sorry, this is equal to lambda alpha on that. Correct? So because I have substituted this, which was our formula for, but this I have this formula. So I can break this up like this. It's the same thing. So I get the same thing. So what have we proved? We have proved that this is itself. It's an idempotent operator. Oh no, sorry, not idem. What's this called? Involution means equals idempotent. Did I say it correctly? Okay. Okay. Idempotent operator. Okay. Okay. So the other thing is, let's work out this is, let's work out its action on in an SL3 case. I want to do that. I want to draw the picture. Okay, but so what I'm going to, but let me write it out. So lambda alpha satisfy the braid relations. We've seen this before. I will not write them out, but I'll just say it. So if alpha, remember alpha and beta are so there is one alpha, lambda alpha for every simple root alpha. Okay. Now if alpha and beta are simple roots such that in this alpha beta check times, if you look at the portion of the Cartan, generalized Cartan matrix with alpha beta, alpha check and beta check on the rows and alpha beta on the columns, and if you see that 2 by 2 matrix that is generated by those 4 points, it will be 2 and 2 on the diagonal and some integers here, right? Okay. Now if you read Katz's book, for example, you will see that there is S alpha and S beta will satisfy a relation only if those 2 integer, these will always be non-positive integers, and only for certain values there will be a relation. Okay, very special cases, some finitely many, it will be either 2 or 3 or 4 or 6, otherwise it will be infinity. Okay. Okay. So again, like in the proof of what did we prove? The while group action on the set of paths, we had to check the braid relations, right? So similarly, you can check that the braid relations are satisfied. Okay, so I am not checking that. It's a I looked up to see if there is a good proof, meaning nice proof, but I couldn't find one. So it looks like it is just a hard checking. Okay, so if you have any better, if you are better informed, please let me know. Okay, so let us do the. So I want to draw a picture and let us check that the braid relations are satisfied. So for example, in SL3, for example, S alpha, S b, so lambda alpha, lambda beta, lambda alpha is equal to lambda beta, lambda alpha, lambda alpha.
There was some while group and all those things are there, but here you are only saying that omega alpha satisfy the braid relation. So gamma alpha, what is the meaning of this statement?
Okay, it means, so there are, the while group is defined by 2 things. It is, there are, so S alpha square is equal to identity and certain other relations which we call the braid relations. Those relations are satisfied by lambda alpha. Is that clear? The braid relations refer to those, so the while group is a Coxeter group, and it is, so it's generated by the simple reflections subject to these kinds of relations. Each of the generators is an involution, right? S alpha square equal to 1. Those are certain relations, and other than that there are other relations of the form S alpha S beta to the power m is equal, m alpha beta is equal to 1. Okay, this need not always exist. They exist in certain cases. So if they exist, then this, if they exist, such a relation exists for alpha beta, then for S alpha S beta in the while group, then the same relation is satisfied by, okay, that's the meaning. Okay. Satisfy the braid relations. So correct, absolutely. Absolutely, good point. Good point. Okay, so what Vishwanath is suggesting is, so when we say this, we should think of it like this. It is of this correct, absolutely, in this form. The braid relation may look like S alpha S beta to the power 3 is equal to identity. Okay. Now remember, S alphas were involutions, but these are not. They only satisfy the braid relations. So correct, thanks for the correction. So you cannot, it's if alpha, so but those relations S alpha S beta to the power 3 equal to 1, for example, can be written as S alpha S beta S alpha is equal to S beta S alpha S beta. So when we say the braid relations, as Vishwanath points out, we mean this form of those relations. Each of those relations you have to write it in this. For example, S alpha and S beta may commute, in which case you will say S alpha S beta square is equal to 1. Okay? So then you will write S alpha S beta is equal to S beta S alpha. Okay? And so on. Okay? Now the upshot before yes. No, we are not saying this is an action. We are not saying this is an action, but there is an upshot. Nevertheless, there is an upshot. Yeah, let me say that. So this is not an action, because we don't have. It's not an action of the while group. No. But we do have the upshot is the following: that why is this? So given an element of W, right? So given W, write W as S alpha, S beta, S alpha, I mean something, dot, dot, dot. Sorry, any reduced expression. Pardon me?
Any other reduced expression will use
So it is a non-trivial fact which is true for at least while groups, maybe Coxeter groups also, I don't know, at least while groups, that given two reduced expressions you can move from one to the other using only the braid relations, and not you will never use those. You will never use the square is equal to 1. Okay? Right. Therefore, this follows because the braid relations are satisfied. Okay? And define set and this is well defined because of the braid relations, because lambda alpha satisfy braid relations. Okay, so let me now state the de Mazur character formula. One thing to observe before I even, so we defined the de Mazur module, right? Let us just look at two very special cases of the de Mazur module. 1 second. So lambda, V. So I put a while group element here, right? So if I put the identity element of the while group, okay, this is just UB of the highest weight vector, but the highest weight vector is stabilized by B. So this is just C V lambda. This is one-dimensional space. And the other extreme, so since I am writing this, you may want to assume G is finite dimensional, then this is V lambda itself. These are two extreme cases to keep in mind. Okay, and let me, one more second, Shamik, before I. So let's state the de Mazur character formula. Right, it states the following: character of V W lambda is the simplest thing you can imagine. Yes, Shamik. No. One second. No. For example, let's try. His question is, are lambda omegas idempotent? Okay. Is there can somebody respond? Quick answer, no? Huh? Yeah, lambda W. So for example, if I take alpha beta as my W and take its, I get this. If I try to compute its square, I am omitting the lambdas, right? But this is alpha beta alpha. So this is alpha beta alpha. Oh, alpha beta alpha is alpha. Okay. So this is in the SL2 case. So I am computing this is, so let's put a now lambda. So I am lambda alpha lambda beta whole square is equal to this, which is lambda alpha lambda beta lambda alpha, which is in the case, let's say we are in SL3, this is V of, this is lambda of W naught. Okay, so it's not. Okay. Okay, is this okay? Okay. Now, let us look at this, let's try to understand this in a particular picture. Okay. So what this we are not proving, I am only illustrating by means of this picture. But that picture, with that picture I hope to illustrate one very particular point to be noted about the de Mazur operator, and that will give us that will illustrate the main point in the proof of the theorem. Okay. So maybe I should state the theorem. What is the theorem that we will prove? Right. The theorem we will prove is, so this is the de Mazur path de Mazur character formula, and this I mentioned the paper before, but this is also due to Littleman, 1993. Okay. So what does it say? It says character of V W lambda, okay, is equal to, okay, if this was W naught, I would take all LS paths and all their endpoints, right? Now I of course take endpoints of certain paths, but pi belongs to Ls of lambda, all that is okay. So if I don't write anything else, I will get the whole character without the W. So since I have put a W here, I have to restrict this set, right? And what is this set? The initial direction. So remember, this initial direction is in one of the lambda directions, right? Initial direction must be less than or equal to W lambda. So just look at those paths whose initial directions. So remember, there was this on the conjugates of lambda, there was also a partial order. Okay, so I am using that partial order. So the initial direction of pi. Okay, so let me rewrite it here. Pi is in, so the sum is over all LS paths of shape lambda. Okay, that's a string. Yesterday Shamik was asking why shape lambda, but because of the Tableau language. And then initial direction of pi is less than or equal to W lambda. This is what we want to prove. Okay, and what is the trick? So now we should also expect this, right? So the while group action was lifted to the level of paths, right, which is what we used sort of to prove the while character formula, that the path version. So what would you expect here? So you would want to lift the de Mazur operators. De Mazur operators acts on ZP, right? I want to replace that P by pi. I want to have it operate on all paths. Okay, and instead of, now the answer will be, so in the case of e to the so I got answers like this, right? This was e to the lambda. Now what will it be? Acting on a certain path will be that path plus something other path, etc., etc. So it will be some, instead of this, it's like I take this and apply various S alpha, the S alpha string, the alpha string through it, right? Sort of the alpha string through it, right? Lambda, lambda minus alpha, lambda minus 2 alpha, etc., right? So now, assuming m is positive, what will I do? I take a path, take f alpha of that path, f alpha square of that path, and go exactly up to the same level as dictated by my, see here how far I go was dictated by the m, right? So I went, if you remember if I start with lambda, I go to minus lambda, meaning if I start with m, I apply m minus 1 times, right? So I start with that, then f alpha of, I decrease alpha once, I decrease alpha second time, I decrease to get here, I decrease by, in m, from lambda to minus lambda is lambda minus 1 steps of 2, correct? Did I say that correctly? From 1 to minus 1 is precisely 1 step of, lambda steps, I should say. Okay, sorry, lambda steps. Okay. Anyway, so that will be the definition. And once again, from it is clear that this is a lift to the level, it will be a lift to the level of, so if I take the map from pi to p, sending a path to its endpoint, this will be, lambda, this will be this invariant. I can take this, apply it to a path, and then send it to the other side, or I send it to the other side and then apply the operator. It will commute with the de Mazur operators, this restriction, this map, where I send from the paths to the endpoints. Right, that will be a property. Then what will be, all I need to do is then observe that the paths have a certain very beautiful property, and to illustrate that property, I am drawing this picture. Okay, so this picture will serve several purposes. It will show you why this will give you the, for example, when W is equal to W naught, this will give you the character formula, Weil character formula. I mean, this will give you the whole character of the entire module. It will illustrate that. It will also illustrate why the braid relations hold in a particular case. Okay. It will also tell you the idea of the proof. So there are many reasons for me to draw this picture. Okay. So let's draw a picture. As you must have realized, I am fond of drawing these pictures. So this is our standard picture, epsilon 1, this is alpha, this is alpha, this is beta, this is beta, this is alpha. So this is H beta, and this is H alpha. So you must have noticed Mrigendra is very good at drawing parallel lines. Since I cannot trust myself to draw parallel lines, I always have to draw these triangles. This side. So I got it wrong. Uh-oh, that's not right. Okay. Let us do, is this a good thing to take? Okay, let's take this. I think we have taken this weight several times. 3 epsilon 1 plus epsilon 2. Okay. So let's, this is my lambda that I start with. Okay. So let us first try to see what happens if I apply. I want to, let's start by wanting to check the braid relations, right? Okay. So what does it say? Alpha beta alpha is beta alpha beta. Okay. For convenience, I'll just omit the lambda. I won't keep saying lambda. What I mean by alpha beta alpha is lambda alpha, lambda beta, lambda alpha. Okay. So I apply alpha beta alpha or beta alpha beta, I must get the same thing. Okay. Is this clear what we are trying to do? Okay. So let's start doing it. So okay, so maybe I'll try to use colors. I don't know whether I'll succeed very well. So this is my initial point. Suppose I apply the lambda beta to it first, the De Mazuri operator. What will happen to it? So I must decide what my m is, right? What is m? M is 1, right? B is just the distance from this h beta. It is 1. So what will happen to it? It will give me 1 minus 1. Minus 1 here means you reflect, you subtract beta and keep going until you hit the reflected point. Right? Okay. So, okay, I draw that first level in green. Okay. Now I must, so is this okay? First level is done. Okay. So what do I do now? I must apply S beta or lambda beta. Lambda alpha. Lambda alpha. Okay. So how do I apply? So that is, I look at what these are in terms of distances from here, right? Okay. So how far is this? This is what each step is distance 1. Okay. So this is, and this is the positive sign. This is the negative sign, right? Because this is our dominant Y chamber. Okay. So this is 2. So I must do 2, and then I must subtract alpha. Alpha is going in this direction. So alpha is going in this direction. So if I subtract alpha, I get here. And then up to -2. Okay, very good. So do we all agree that I will draw this in white? That's what we get. Correct? Okay. Now, similarly for this, if I start applying, so please tell me what do I get? This is how far from here? 3. So I must get 3. Next step is 1, then -1, and minus 3. Okay, this is what we have. Okay, now the last step, I apply beta again. Okay, so I apply. What happens here? Here, of course, I can do it again, but instead of doing it like that, I can say on this whole thing, this was the application of a beta. But if so to this pair, if I apply it again, nothing will happen. That is, if you have, so if it already looks like an SL2 module weight, then nothing will happen to it. You can forget it. Okay. Then what about this one? Beta value is 0. So what happens to it? So think of the character of the 0. Nothing happens to it. It just is identity on that. It just gives you back that itself. So it just gives you back this itself. Okay. Now let me start putting a tick on it. So we are done with this. We have to do this. What does this give me? 2. Therefore, this gives me this, and this, right? Okay. So this, which I don't need to write, so I'm going to tick this and this. Pardon me? Yeah, this, because there is one that I get from this, and this I get again from this. I hope you understand this. Right? Okay. How about this? This will give you this, right? And I'm done with this. So this will give you this and this, more precisely, this and this. Okay. What does this give you? This, then this, then this, and then one more. Okay. So we are done with this. So the only thing that remains is this. Okay. And what does that give you? It's what distance? 2. So this is this. Sorry, I should draw. And this. That's the picture we get. No, we didn't quite it. So the white. So luckily, I have drawn. No, this is not white. This is okay. So the blue and green ones so the blue, green, and the white dots are the ones on which we need to compute. That's what we had. Blue is what we started with. Blue and green together is what we had in the first step after application of first beta. The blue, green, and the whites were what we had after applying beta and alpha. Okay, so is this, that's the picture. And from our experience of characters now, you can see, I think Mrigendra calculated this. This is 15-dimensional, and there are 9 plus 6. We did this several times. Okay, so this is the full module. Okay, so this illustrates that you get the character when I apply the W naught. Right. So far, our only experience with the characters has been with the full module. Okay, but yes, what's the confusion? What is the conclusion? No, the conclusion is that when I put W equal to W naught, this side gives me the, if I apply this observation, then this is character of V lambda. So I could have done this, drawn this picture. After you practice, you can draw this picture very quickly, alpha, and that's a way of producing the character of the entire module. Because in the SL3 case, S alpha, S beta, S beta, S alpha, S beta, or S alpha, S, is W naught. This is just meant as an illustration of the claim that when I put W equal to W naught, I get here the character of the whole module. That's all. I'm not claiming anything deeper than that. Yes, depending on which lambda you start. If you start with a dominant lambda, you will get, so this is lambda dominant. Thank you. I'm starting with a dominant lambda. Any dominant lambda. Any dominant lambda, you start and apply this, you will get. Okay? So, let us do the other way. Right? Let's do the other way. Maybe on a different, let's do it on this same picture. Okay, very quickly. So if I do the, so first I did the betas, but now let me do the alphas, right? Alphas will give me this, this and this, correct? Okay. Now when I do the beta, then this will give me this will give me these 3 dots, this will give me these dots, but these are not there. Okay, so I'll get these dots, but without the multiplicities here in these places. Right? Okay, what did we do? Now I have to apply alpha again. Okay. So this will give me this. This dot will just give me back itself because it's on H alpha. This will give me this, this, and this. So I get this multiplicity too, and I get this back. Okay. Now this will give me this whole line, right? That whole line. This will give me these two, correct? Or rather, the combination of these two will give me back those two. Okay, so I got the multiplicity here twice because I got them once from this, and the combination of these two gives me back that. Okay, and what else did I have to say? And finally, if I apply to these 3 and S alpha again, nothing will happen because it's already S alpha applied. Okay, so by this property, what is happening? So I'm given a bunch of weights. Okay, so let us concentrate on this. So let us look at this last calculation once again. So I first what did I do? I applied an alpha and then a beta, right? So I first got I have all these weights, but without the multiplicities. right, without the multiplicities. So what do I have? So let's draw this picture here. So in terms of the weights, and what am I going to apply? I'm going to apply alpha at the end, right? I'm going to apply alpha at the end. So this picture, the multiplicity for alpha is as follows, is 2, 0, minus 2. That is from this. This is 2, this is 0, this is minus 2. Okay. I have another. So what is this? 3, 1, minus 1. I have 3, 1, minus 1. Okay. And what is this? Minus 3 was not there. This is before applying the last step. This is before applying the last step. I only have these dots and without the multiplicities. Yeah, I have applied S alpha and then an S beta, and I'm yet to apply an S alpha. Okay, okay. And what is this? This is 0, this is 2, and this is 1. So there is a 0, there is a 2, and there is a 1. Okay. So if you analyze what is going on, anytime, so okay, what is this? This will be a B module, always. De Mazur, they are always B modules because they are defined as B modules. Okay. So this will be stable under. So what you have is you concentrate on. If I want to apply alpha, I concentrate on the SL2 alpha of it, right? It is meaning it is not, what is given to me is not an SL2 alpha module. I am trying to make it into an SL2 alpha module, so to speak, but it is a X alpha module, meaning X alpha, it is stable under X alpha. Okay, is this clear what I am saying? It is stable under all X's, in particular X alpha. Okay. So if once I apply a how to say this, after I have applied a beta, it becomes stable under Y beta as well, but at any level it is always stable under the X's, because that's the way UB has all the X's. Okay. So in this picture, when you see, the upshot is, if there is a negative point, minus 3, then there is a corresponding minus 1, minus, it will be, if I start with negative 10, then I must have negative 8, negative, all the way up to 10. Okay. But positive ones can occur separately. So in other words, I should always be able to break this up. So this is an elementary statement about UBSL2 alpha modules, if you wish. Whenever you have a UB module, just for H and X, just imagine an H and an X, and if it's stable under that, look at the weights of that, a finite dimensional module, look at the weights of that, what will it be? Whenever there is a minus 2, there is always a 0 and a 2, because I can apply X alpha to it and it's non-zero. And if I started with minus 2, I can apply it twice before it may become 0. So that much I am sure. So you will always be able to decompose this as pictures involving full SL2 modules and certain non-negative things. So what will remain, there won't be, after you have paired this off, there won't be anything negative remaining at all. Okay? Or in other words, you cancel every negative with every positive. Okay? If I have a negative, just cancel it with the positive. This is for the beta. I mean, sorry, last S alpha, sorry. What did you want to do? This is alpha check, yes. Okay, you have already applied beta. So when you do it, it will look like entire strings. See, this is the step we were in. See, this is what we started with, right? If you so what would you do? First we took alpha. When we took alpha, you got this string. 1 second. Now, when you have applied the alpha, it looks like, if I look at this picture, it will look like 2, 0, it will all be complete. There will all be full strings from m to minus m, always. Is that clear? After you have applied that. Okay? So when I apply beta to this, you see I am getting 3 strings. After application, it will be complete. Okay? But what the de Mazur thing is saying is, you will always be able to pair the negative with the positive, throw them away, okay? But also I should be more careful, because I should not say it that way, because the 0 should also go, okay? So rather you throw away whenever you see a finite dimensional weight thing there, you throw it away. Okay, and so that what remains is always only non-negative numbers. Okay, and then you complete it. That's all. So if there is this 3 here, maybe it's some. Remember, we are doing this in that it may be some mu. This may be some mu. This may be some, because this is only the alpha check value, right? The weight may be something. So mu1, mu2, etc. Mu3, mu4, that's what remains. Now you just apply the S alpha. So for example, this will become E mu1 minus alpha, mu1 minus 2 alpha, mu1 minus 3 alpha, because you complete it to the string. That's what the de Mazur operator is doing. You complete it to the string, but here you don't get anything. Here if you complete it, you will get 2 things, right? Here if you complete it, you get 1 extra thing. Okay, this is the picture. Yes, Satish.
Precisely because you started with the element in the dominant y check.
I don't know if that is important, because otherwise I'm not sure that is important so much. But anyway, we are always starting with the dominant Y chamber. Okay. So for the moment, I'm not sure that is required, but anyway, let's not worry too much. Lambda is all. Yes, Satish, you had a question. Which 2 should come above? Huh? No. That's, see, above 0 meaning, in this picture it is above 0, but that's not the way I'm looking at it. In this picture it's above, see, so I just look at all the weights, I throw away full SL2s. I just look at it as a set of weights. So this 2 I could have kept this 2 and cancelled this 2. Doesn't matter. Sorry. Okay, I see what you're saying. You mean this one was e to the mu2, so this 2 was e to the mu2 minus alpha, you're saying. This was actually here, you're saying. Okay, take it there, doesn't matter. I was being more general. Okay, this will not give me anything new anyway. I will just start with this and get this string. Ah. Why is this? Whether you remove the 0 or don't remove the 0, it doesn't make a difference. Okay, you want me to remove the 0, I can. But what I mean by that, okay, good point. Sorry, I should have been more careful. The way I said it, maybe I should have removed the 0 also. Okay, but whether I remove the 0 or don't remove the 0, it does not matter. Because what is the final answer? The final answer is you keep this aside, you keep the full things aside, and you take these, the ones that do not belong, and complete them. That is the picture. Okay. Now, if 0 I decide to keep it in here, I decide to complete it, I get back only 0. Okay. If I decide to keep it here, of course at the end I also add these things to what I had, to what I get. So in other words, these are existing already, I keep these, and the new ones are these new dots that are generated. Is this clear? So this 0, whether I put it here or whether I keep it here, it doesn't make any difference. So you choose which you want. 0, if I think of it as negative number, then I pair it off with itself and put it here. If I think of it as a positive number, I keep it and generate extra things, but it doesn't generate anything except itself. So is this clear? It doesn't matter how you treat it.
You are not trying to prove that lambda alpha, lambda beta, lambda alpha is the prime relation you are trying to prove?
No, that I assume we did because I get back the same picture. By the illustration that we did, I'm not trying to prove that. I'm not trying to prove that. I'm just illustrating a certain point. So the point is, how do I apply? No, this is not the proof. I am just saying this is the way I'm just saying. I'm showing you that this is how the De Mazur operator is operating. So suppose I am at a certain situation. So I'm going to do this by induction on W. Suppose I am at a certain level and I have come up to the, so okay, let's come to the proof of the theorem. I want to prove this. I will start with W equal to identity. Do you see in that case? In that case, this is just this trivial module. And the initial direction is in the direction of lambda. If I start in the direction of lambda, I just keep going up to lambda, because remember, this is a rational, what was called a rational path, meaning the direction, you start some direction, then the next direction you go must be bigger than or equal, less than or equal to that. So if I start with lambda direction, nothing less than that. So nothing is less than that. So I keep going in the lambda direction, right? So there is only one, this is just pi itself. And so I get that. So it's checked. So now I do by induction on the length of W. Okay. Suppose, so I write, okay, so here is the proof. I erase this picture, but keep that picture. This picture here. So proof. W equal to identity, this is okay. So induct on length of W. Write W is equal to S alpha V, say, okay, with length of V equal to length of W minus 1, standard, okay. And by induction, you know that by induction, you know that V of character of V lambda is equal to the set of all pi in Ls of lambda. Initial direction is what? Less than or equal to V lambda E of pi 1. Okay, this is what we have. Okay, now what do I have to show? I have to show that if I apply, so by the de Mazur character formula, I know that what do I want? I want, remember, I want to prove this for character of V W lambda, right? But this is equal to this applied to character of V V lambda, because this is one length more, okay? And I already have this. So I am reduced to apply, yes? This one? This is because if this means that a reduced expression for W can be written as a reduced expression for V and added on an alpha. Okay, and if I act the lambdas corresponding to this by the de Mazur formula, which we are assuming, that gives me the character of, so the character of the de Mazur corresponding to this is the sequence, you take a reduced expression for W and write the corresponding operators, right? But up to the point I get to V, if I write, I get the character of V by the same formula. So is this okay? Okay. So, and then I have to apply to the right side and show that. Okay. Now, here, and this is where the point comes in. So I have to analyze what happens. If you draw the picture of this, if you think about the picture of this, you have to think of the alpha weights of whatever you see, of the vectors there, of what you see there. And that picture, I claim, will look like this, in the sense that, remember that it's a B module. Therefore, you can always write it as a sum of full, so the weights will be full, okay, and there will be the remaining weights. The remaining weights will be all positive or non-negative or positive. If I was saying non-negative, Satish prefers positive, you can take either, both are correct, okay? Because 0 I can keep or not, I can put it either to this side or this side, it doesn't matter, okay? So is this okay? Okay. So now the key thing is the following. I will define an operator on paths, this de Mazur operator on paths, which will mimic this, right? Remember, we wanted the while group operation, right, on paths. How did we do it? What is S alpha tilde of a path, right? What does S alpha tilde do to a weight? You just saw that, right? If it is M, then then you subtract M alpha, right? S alpha from the, if it is positive M, you subtract M alpha. And that's why what we did was, if the M was if the endpoint evaluated to M on alpha, then I applied F alpha M times. That was my trick, okay?
That is correct. Take the oral plus SL2 of alpha.
Hmm.
Then if you consider that how did you generate the pattern? So that whenever
Yes.
positive occurs, the negative also will occur.
Rather the reverse. Whenever negative occurs, the positive will also occur. Yes.
That is fine.
Yeah.
But here in this, for example, VB of lambda that we have taken, also that may not be.
No, see, so when I see this,
So we may not have this alpha in the support. So may not be.
no, doesn't matter. Doesn't matter. At any given point, see, it's a B module. It's always a B module at whatever point. Say alpha may not be in the support of, if for example in the beginning, it is just some positive number, that's all. Lambda alpha check, it is just that one positive thing, that's all.
Then if I apply lambda alpha,
You will get the, no, this is before you apply the, so this was the picture before I see.
why the multiplicity will match? The 2 is there.
So, okay, maybe.
You want to divide the weights into.
Yeah. So what I am claiming is, so here is, let me write this out and maybe we'll stop here, continue tomorrow. So let V, or let's call it the U, be a finite dimensional U B SL2 alpha module. Okay. So, or let's be more okay. Is a finite dimensional B module. So B is equal to B of SL2 alpha. SL2. Okay. This is clear. It's generated by X and H. Okay. Let U be a finite dimensional, okay, U be a B module, let U be a B submodule, let's be careful, B submodule of a finite dimensional SL2 module. Let's make that. See, it's a submodule, but the whole thing is an SL2, finite dimensional SL2 module. Okay. Then what do the weights you look like? That's the question. So let's assume that.
What is that here?
For example, after I apply the SL2, if you wish. After I apply the SL2, or see, if I take a set of weights, given any finite dimensional module, it is contained in a finite dimensional SL2 alpha module for any alpha, given any finite, take such a thing. So take my de Mazur, so I take this de Mazur module, which is finite dimensional. It is contained in some finite dimensional SL2 alpha module, correct? I take that. Yes, that is, I am just saying that is just. After I complete, not before I complete, because for example.
Once you apply lambda alpha,
yes. Okay, so maybe we should call this a day. I will continue tomorrow. Okay.